All right, everybody. So today we're actually going to learn how to do something we've referenced quite a few times. We're going to talk about how we turn those analog signals into digital data so that we can manipulate it. So the primary or the piece of hardware that actually performs that conversion of analog to a digital signal is called, unsurprisingly, an analog to digital converter, also commonly known as an ADC. So, as we've talked about previously, our analog signals are continuous, constantly varying quantity, right? And we have to basically turn that particular voltage, is what we're usually talking about, a voltage signal, into a discrete set of numerical values. That's all that a digital device value is. It's a discrete set of numerical values. That's what the digits are. So, right, most of our actual real world signal outputs are going to be time varying, continuous analog waves, right? They're going to be taking some random voltage that changes with time. But if we want to do any sort of computation, if we want to store it in a computer, if we want to write it to an SD card, if we want to display it as a number on a screen, we have to convert it basically into a binary form readable by the computer, right? So that is what the ADC does, is it takes your analog signal as an input and it outputs a digital signal. And usually what we mean by that is it outputs a number at a particular, for the value of that signal at a particular point in time. So as you can imagine, you pretty much use this almost everywhere. Any sort of microphone that you're going to record sound with is going to use an ADC. The oscilloscopes, unless you were using an old cathode ray tube oscilloscope, you were probably using a digital oscilloscope, which means it had to convert the voltage that you were hooking up to the channels to a digital signal. Basically, any sort of actual device is going to have any sort of measurement device is going to have an ADC. Your multimeter includes an ADC because if you have a digital multimeter, it's outputting, a finite number of digits. So it's converting that to a digital signal, but whatever you're touching it to is probably just a analog voltage. So all of our sensing devices that we're recording with we're digitally recording an analog world, right? So basically any sort of modern sensor, somewhere in its stream from input to final output, there's going to be an ADC at some point. The Megasat, which is the board that we provide you guys for your base payload, is going to use an ADC to measure temperature and humidity, as well as pressure. All of those sensors output an analog voltage, so you're going to have to read those voltages in with the Arduino. So how does this actually occur? So if we take just an arbitrary analog signal, and in this case, we've just drawn a cartoon picture of a simple sine wave. So at any point in time, you can have it could be at some voltage from this max value to this min value. So first, we need to slice it up into individual time sections, right? Each one of these we then divide up, right? Because we can only have a single number at a single point in time. And we don't have an infinite amount of time slices. So we're going to have some sectioning that we're going to do into individual times. And then basically within one of these smaller intervals, we're going to sample the voltage at a particular point in that sample, right? And that's what we're going to call our sample. The voltage that it was at that particular point in time. So, and then we're going to convert that one voltage into a number. So that's how we're going to turn one of these continuous time varying signals into a sequence of numbers. So once we pick a particular voltage, we actually have to turn it into a digital number. And the way that you do this is that the voltage is compared, the voltage sample, right, that single value that may have any particular voltage number is going to be compared to a bunch of discrete voltage steps, sort of like on this graph on the right. And each one of those discrete voltage steps that goes from some minimum voltage to some maximum voltage within that step is going to correspond to a particular integer value. So from, like, for example, you can see here from what is about 0.03 to about 0.6, that corresponds to the digital integer value of 1. So the ADC is basically going to go through and rapidly compare your analog signal, which is this red line here, and it's going to find the two voltage values that it falls between. And it's going to then output a digital signal, which will be the binary representation of whatever this number is. Now, how that circuit actually does that, there are several different techniques that you can do. If you were to look it up, you may see something called a delta sigma ADC. There's kinds that basically have a whole bunch of voltage dividers, and it just compares each one of these until it finds the largest, till the one it matches closest to. There are many different types of ADCs in how the chip actually works, if you were to look into it on a very low level. And those are going to give you different amounts of resolution, i.e. I can break this up into smaller and smaller steps, or they're possibly going to do that comparison more quickly so you can more rapidly find out what that value is. Some of them will have different amounts of noise. This is all stuff that if you were designing and picking a particular ADC, you would want to know so that you can find the right type. But one thing that's important to note is that this process does take time. It has to check this one, nope, this one, nope, this one, nope, this one, yes. And the other important thing about it is your values come in those discrete steps. Just based on the output of the ADC, I don't know where within this particular voltage bin the actual signal was, because all I get is this 3, which means it could be anywhere from 0.1 to 0.13. And that is what we call the ADC resolution, right? It's the smallest, it's how well you can resolve an individual voltage based on what the ADC value was. So obviously, if I take the same voltage span, so ADCs will be from a particular minimum voltage to a maximum voltage. In particular, the Arduino is a 0 to 5 volt ADC. And if I have a larger number of integer bins, if I have more possible values, each one of those will span a smaller amount of voltage, so I'll have a higher resolution. The one on the Arduino Mega is a 10-bit 0 to 5 volt ADC. So the way that you calculate how many individual voltages you have is you just take the number of bits and raise it to 2 to the n, right? So if I have a 10-bit ADC, that means I have 1,024 possible ADC values. I will get values from 0 all the way to 1023. And each one of those is going to correspond with a particular small range of voltages. In particular, the 0 is going to be about 0 volts, and the 1023 is going to be about 5 volts. But one thing that is important to know is those are not exact. It's not going to be perfectly 0 and perfectly 5, which means you're going to need to do, even if you were doing a pure voltage measurement, you would need to do a small calibration to find out, what is the slight shift from that minimum and maximum value. So the actual resolution of a single ADC is just how wide each one of those little voltage bins are. And that's fairly simple to figure out. You just take what's the maximum voltage, i.e. what's the value at 1023, minus the minimum voltage, i.e. the value at 0 ADC, and you divide by the total number of ADC. So in this case, 5 minus 0 over 1023. So in particular, that gives me a resolution about 0.005 volts per bin, right? So each little step is 5 millivolts wide. So you can get ADCs in multiple or all kinds of different resolutions. You can get, 8-bit ADC is fairly common, 10-bit, 12-bit, 14, 16, right? But all of these, so they're going to take more memory to store the value, right? It takes more space to store a 16-bit number than it does an 8-bit number. And there's also going to be some trade-offs in how quickly you're going to get outputs out of your ADC. So often you are going to want to go backwards as well. Because you'll likely record ADC values in your program or to your data storage, and you're going to want to be able to convert that back to the voltage. Well, again, we can just take the ratio, right? We can have, here's the number of ADC bins over the system voltage, so that would be like 1023 over 5, and then the reading over the actual voltage, right? So that's fairly easy to calculate. So for example, if I had a particular ADC value of 434, well, that's going to correspond to a value of 2.121, right? Plus or minus that width of that bin, because I really don't know exactly where it is, right? So that's why you always want to remember, hey, how wide are these discrete steps? The other important thing with the other than the resolution, the other spec that you really care about is how long does it take that conversion to happen, right? So you're going to sample that voltage, you'll do the conversion, and then you'll get the output. But there's nothing that is, your input signal is not necessarily steady during that entire time. It could be changing. And the amount of time that conversion takes is basically, that's going to be sort of an upper limit as to how often you can actually sample your signal. So you need to have some idea of how quickly the signal is changing so that you can have an ADC that can sample it fast enough so you can see the changes that you're looking for, right? So if I'm looking at a voltage signal that's going to take 5 or 10 seconds to reasonable change by a reasonable amount, well then my ADC, which is probably going to be at the very slowest on the order of milliseconds, I'll be fine. I'll definitely be able to see those changes. But if I'm looking for something that is changing on the order of microseconds, well, now I probably need different hardware than just a really cheap off-the-shelf ADC, even though a lot of those are actually quite fast these days. So it's just, you need to have an idea, again, of what range of signal you're going to see, how quickly it's going to change. You can't just go in blind and assume you'll be able to pick the right circuit to do the job. So we call how often that we can actually sample, that frequency, we call that the sampling rate, right? It's the rate at which sampling occurs. And in particular, if we go back to our just simple picture here, it's sort of basically how spaced out are these vertical lines. That's the sampling rate. So the ADC hardware and your microprocessor, they're going to set like an upper limit, right? If basically there's a max rate of how quickly I could possibly read in an analog signal if I did nothing other than try and read it as quickly as possible. Odds are, for the stuff that you're going to be working on in here, you don't need to be doing sampling at that quickly, right? And in particular, if you're doing that, if you're sampling at that maximum rate, you're not doing anything else other than reading an analog pin, other than sampling. You're not storing that to permanent data storage. You're not doing any math on it. You're not checking other sensors, right? So you're going to have to figure out what is the actual sampling rate that you need based on what you're trying to observe, right? That's what this science requirements are going to tell you, what the actual sampling rate you're going to choose. Those are somewhat going to be affected by how quickly you can sample and process and store that. And then obviously, if I'm storing a fixed amount of times worth of data, like the data for a single payload flight, if I sample more often, I'm going to need more storage. Now, storage capacity these days is not really as much of an issue as it was, because, good luck finding an SD card that's smaller than 32 gigs. But when you were using something like a 16 kilobyte flash memory for storage, you were thousands of bytes smaller, that was a lot more of a concern. And if you're working on a very advanced, scientific payload where you may be sampling a lot of stuff over a long period of time, over like a month's worth balloon flight, then that stuff may become an issue again, right? But at least for the payloads you guys are going to build in this course, you're probably not going to have to be concerned about storage capacity. So there is also a practical concern about, well, why don't we just make the sample rate as high as possible, right? Well, you could do that. You could get some really accurate data, but you're just going to make your life more difficult, right? You're going to have to do analysis on this data. So you are going to have to figure out some way to deal with it. And if 100 data points effectively gets you to the same conclusion as 10,000 data points, it's a lot easier to deal with 100 data points. So also you have practical hardware limitations. You have only so much space in memory. And the processor, you probably want to do things other than read out a single sensor's analog values, right? You're going to want to go check your GPS. You're going to want to write your data to the SD card. So all of this is going to drive you to try and figure out what is the actual amount of sampling and precision that I need. So it turns out there's actually a mathematical theorem that says, hey, if I'm looking for a signal that takes this amount of time or has this frequency, you need to sample this often. And it's actually pretty simple. It's called either Shannon sampling theorem, also called the Nyquist sampling theorem. It may be called the Shannon-Nyquist sampling theorem. But basically it says that you need to sample twice as quickly as the highest frequency that you want to try. So you could pretty easily guess that based on your sine wave here, right? So if I'm sampling this sine wave at the same frequency, well, I'm basically sampling this wave in the same spot every single time, right? So let's just say, for example, I happen to match up on the peak here. Well, if I'm sampling this every single time on the peak and no other time, well, it's going to look exactly like a DC voltage, right? Because I'm just picking it at the same time. Whereas if I'm getting it at twice the speed, well, I'll get here and I'll get the peak, right? And the idea of that is you can see those actual variations. Right, so you want to get basically, you want to see it go, in one sense, start at its maximum, see it go to its minimum, and then see it return. So that's the idea here, is this is the minimum sampling rate you need to actually be able to see that something is happening at that speed. If you want to see more details, you'll increase that by somewhat. So functionally, how do you actually do this? Well, you start with what is the actual thing, the science goal that you have, what is the thing that you're trying to measure, and what is sort of your expectations of what that particular piece of data is going to do over the experiment or over the flight or the observation. What do you actually want to measure? You want to also compare that to what is your processor able to handle. And in general, you should pick a microprocessor or a sampler, sensor, or an ADC based upon what your actual requirement is. And in addition to the microprocessor, you want to make sure that you have enough digital storage so that you can actually store the data that you're going to sample. So let's just run through an example of how you do this. So let's say, all right, we're trying to observe temperature during a balloon flight. And for whatever reason, I only care that my temperature is accurate to a single degree. So my science requirement would be, I want to observe temperatures from ground level all the way up to 100,000 feet. I want to be able to see changes of a single degree or larger. And then I need to be able to store this data in a way that I can actually read it later. So I'm going to store that temperature number as a plain text ASCII file. And this is going to help me pick, how much storage do I need? How often do I need to sample? All of that stuff. All based on these 3 requirements. All right. So you got to do some research, right? You have to look at, okay, what is the sort of changes that I'm going to see in an atmosphere? Because if you just say, well, I don't know, you'll basically be randomly picking a set of ranges, and you may get lucky, but it may be that you'll pick a value and then you basically max out your ADC in the first 5 minutes of flight. So you do some research, you look at, okay, what does the standard atmosphere show the maximum rate of change with altitude is? And then I can, expand about that a little bit, but you look it up and you say, okay, what I'm most likely, the fastest temperature change I'm likely to see is 3 degrees every 1,000 feet. Okay, so now I need to know, okay, well, how quickly is the payload going to be rising through the air? Usually that's around 1,000 feet per minute. And how long is the flight? Well, it's going to be, the actual flight is something like usually 2.5 hours, 3 hours, but we want to build in some extra time because we're going to get turned on the ground and we may be sitting there for a while. So we'll just say that we want to make sure we have enough data storage and capability for 4 hours of data. All right, so using the 3 degrees per 1,000 feet and the 1,000 feet per minute, well, it's pretty easy to figure out how quickly we're expecting to see the temperature change. And that's just 3 degrees a minute. Easy. Next, from that same sort of standard atmosphere, we can look at, okay, the lowest temperatures we expect to see is maybe 50 degrees, negative 50 degrees. Sorry, that's actually the negative sign right here. And, we're going to be sitting on the ground in a piece of electronics in the hot sun. And then also when we're above the atmosphere, we're sort of going to be insulated. So we'll probably see temperatures maybe as high as 50 degrees. So based on the fact that my temperatures go from negative 50 to positive 50, I can then be like, okay, I need 3 bytes. I need 3 characters for each individual temperature. I need a plus and minus, and I need the 2 numbers. So that tells me each one of my data points is going to take 3 bytes. So I'm going to take a data point, so that I can see all of these things, right? So this is going to drive how often I look at my ADC, what sort of amplification circuit I use. All of that's going to come from these numbers. All right, so first, let's start at the sampling rate. All right, so we said we wanted to see 1 degree per change. And then we also said it's going to change 3 degrees a minute, which is also 1 degree every 20 seconds, right? So if I divide 1 minute by 3, that gives me 20 seconds. And then also, so that rate would be 0.05 hertz. But as we said earlier, I want to sample at least twice as often. So I'm going to sample at 0.1 hertz, right? So that means as long as I look at the temperature every 10 seconds, I should not miss a change of a degree because it's not changing that quickly. All right, so how much storage space do I need for all of this? Well, I want to make sure I have enough space for 4 hours. I just need to do the conversion to seconds, right? I then say I take 0.1 sample every second, or I sample at 0.1 hertz, right? A hertz is just a cycle per second, a sample per second in this case. And each one of these samples is going to be, each one of these data points is going to take 3 bytes. So that means that to store all of this, I am going to need, a little bit more than 4 kilobytes. I have left off some other stuff. For example, I probably want to be able to have some sort of character in between each data sample. And obviously, there's probably in the end going to be more other data that I'm going to want to collect. But just for the simplicity of this example, that's sort of what we've chosen, right? So yes, I have a question here in the room.
Why do you have 0.1 sample per 1 second?
So that's what a hertz is, right? A hertz, in this case, it's things per second. So it's often waves per second or cycles per second. But in this case, we're talking about samples per second. Obviously, I'm not taking part of a sample every second, right? I'm taking one sample every 10 seconds, but that's the same number here. So if I made this a 1 and I made that a 10, that's the same thing, right? So I can also use this same sort of math to figure out what my signal conditioning, my amplifying circuits are. So if you remember, what we talked about is the signal conditioning is what we're going to use basically between our sensor and our ADC readout. And it's going to convert a sample, a signal that's difficult to read, it's not in the right range, and we're going to get it to match. So we can either increase or decrease it, right? And we generally want to match it so that we're actually using the entire or the majority of the range of our ADC, right? If my signal input is only 0 to 0.1 volts, but my ADC is 0 to 5, right? I'm not using all 1024 bins. I'm only using a very small portion of it. And the way that we get around that is we'll amplify it so it matches better. So if we sort of go back to the example we've been working on, if we just look at the ADC, like we said, its resolution is about 0.005 volts, right? So what that means is if we want to be able to see a single degree change, is our sensor and our signal conditioning output that leads into our ADC, that signal on the output side has to change by more than 5 millivolts for every degree of C. So that's sort of says this is the minimum of how big our signal change can be. Now, we also said that we want to look at temperatures over a range of 100 degrees C, right? We want to look from -50 to +50 C. And again, our ADC is 0 to 5. So if we say that we can't have a voltage change larger than 5 volts based over those 100 degrees, right? If we take 5 volts and divide by 100, we're also going to set a say that our signal conditioning output, our signal that we're finally feeding into the ADC, it can't change more than 0.05 degrees per degree C. If it changes more than that, we'll basically either max out our ADC on one end or minimize it. Our signal will go outside of the range where we can actually measure. So these two numbers basically sort of tell us how quickly our final amplified circuit or amplified signal has to change. Yes, I have a question.
How do you calculate the last number? Like the maximum?
Oh, that's simply that. So I have 5 volts span, right, in the ADC, and my temperature span is 100. So it's just 5 divided by 100. So. All right. So let's say I know a little something about my sensor, and I know that it's going to read out 450 millivolts at -50, and it's going to read out 800 millivolts at +50, right? This sort of depends on you knowing exactly what the signal output is going to be. Often there's going to be some uncertainty on this. So you may have an idea of what the ranges are, but you won't know the exact values. So you'll want to have your amplifying circuit so that you can actually adjust the gain and the offset slightly so that you can basically pick initial values and then make small changes. But if you remember from the amplifying signal conditioning lecture, we have the base value is the minimum value, 450. The span is 350, right? It's 8 minus 450. So I'm going to decide that I want, so this is the input to my signal conditioning circuit, to my amplifying circuit. I want the outputs to be 1 to 4 volts. So I want it at 450 millivolts to output 1 volt and at 800 millivolts to output 4 volts. Now you may ask, well, why didn't I go all the way 0 to 5? Well, I probably don't want to go all the way to the ends unless I need it, because I want to make sure that I'm a little bit clear of those limits, right? Especially if I'm going to have to go back and adjust. So in this case, that has a base of 1 and a span of 3 volts, right? So if I look at what that actual change per degree is, if I do the math, I can calculate that at the output, this is going to give me a change of 0.03 volts per degree C. And yep, that is less than this number and greater than this number. So that will actually work. And if I take these two sets of numbers and I calculate the line, right, I can get that transfer function that will give me the value that I need. And, you know, this is just the particular values. So what I would then do is I would look up the appropriate type of op-amp circuit. In this case, it's a non-inverting amplifier with offset. And then I would find out, okay, these are the particular resistance values that I need to build into my circuit to get this output. So we've talked about the ADC sort of in general, but how do you actually use this on the Arduino? Well, actually, it's very, very simple. There's a function called analog read, similar to the digital read, right? And you just tell it what pin that you want to read. And then it'll return a number from 0 to 1023. That's your 10-bit value. However, one thing to note is even though the ADC is 10-bit, the actual memory architecture of the Arduino doesn't work. It works in chunks of 8. So it's going to return a normal integer, which is going to actually take 16 bits of memory space. It's just a weird consequence of when you convert from the actual ADC circuitry to the memory circuitry of the Arduino. So remember, you've got 16 analog pins, A0 through A15. So honestly, actually reading it out is one of the simplest things. You just give it the pin number, and then it tells you a number corresponding to the voltage. And that is it. So the actual programming part of this is relatively simple. So that is it for the lecture.